The paper Limits and Powers of Koopman Learning by Matthew J. Colbrook, Igor Mezic, and Alexei Stepanenko addresses a critical question in the field of dynamical systems. When can the spectral properties of Koopman operators be robustly learned from trajectory data, and when can they not? This is a fundamental question because understanding these boundaries is crucial for the analysis, application, and design of algorithms in studying complex systems. Dynamical systems are a key framework in science for understanding behaviors that change over time. Traditional methods have relied heavily on analytic descriptions, but many modern systems are too complex for these techniques. Machine learning has revolutionized our ability to analyze data and predict outcomes, leading to the emerging field of data-driven dynamical systems. In this context, Koopman operators offer a way to linearize nonlinear dynamical systems by mapping them into an infinite-dimensional space of observables. However, practical challenges remain, particularly regarding the convergence and stability of current algorithms. The paper's primary contribution is establishing a foundational approach that combines computational analysis and ergodic theory to determine the limits of Koopman learning. The authors reveal the first fundamental barriers universal to any algorithm, linked to the system's geometry and complexity. They provide examples of systems where Koopman spectral properties cannot be robustly learned, regardless of data quantity and quality. Moreover, they introduce optimal algorithms with verification processes to overcome issues present in standard methods. Koopman operators are a powerful tool in the study of dynamical systems because they provide a way to analyze nonlinear dynamics using linear techniques. These operators transform a nonlinear system into a linear, infinite-dimensional framework, named after Bernard Koopman, who introduced the concept in 1931. Koopman operators act on functions observables rather than directly on states. In a dynamical system, the state evolves over time according to a rule or function. Instead of analyzing the states directly, which can be complicated if the function is nonlinear, Koopman operators focus on observables. Observables are functions that measure some aspect of the system state. The Koopman operator transforms these observables, providing a linear representation of the system's dynamics. For example, consider a system where you observe the temperature at a point over time. Instead of tracking the temperature directly, you could use a function that measures how the temperature changes. The Koopman operator then describes how this function evolves, allowing you to use linear methods to study the system. The main advantage of Koopman operators is their linearity. This linearity allows researchers to apply linear algebra tools, which are well developed and easier to work with compared to nonlinear methods. As a result, Koopman operators have been successfully applied in various fields, including robotics, climate science, neuroscience, and more. For instance, in climate science, Koopman operators can help identify coherent patterns in climate variability. In neuroscience, they can analyze neural recordings to understand brain activity better. In robotics, they are used to control robots more effectively. Despite their potential, Koopman operators have significant limitations. One major issue is that they operate in an infinite-dimensional space, which can make computations difficult and resource-intensive. This infinite-dimensional nature means that practical algorithms must approximate the Koopman operator in a finite-dimensional space, often leading to challenges with convergence and stability. Another limitation is the difficulty in identifying meaningful eigenfunctions and eigenvalues. Eigenfunctions correspond to modes of behavior in the system, and eigenvalues indicate the growth or decay rates of these modes. However, finding these spectral properties can be challenging, especially for complex or high-dimensional systems. The paper provides several illustrative examples. Consider a simple system where a point rotates around a circle. The question is whether this rotation is ergodic, meaning that the point eventually visits every part of the circle. If the rotation angle is an irrational number, the rotation is ergodic. However, determining this from data alone requires taking limits, as you need to observe the system for a long time and compare it to a basis of functions. In this example, if you know the rotation angle exactly, you can determine ergodicity in a single step. But if you only have data from observations, you need two successive limits, one for the time limit and another for the function limit. This highlights the challenge of determining spectral properties from data. This example extends the rotation on the circle by adding a nonlinearity. The system now includes a sine function in the rotation, making it more complex. Depending on the parameters, the system may lose its ergodic property, requiring an analysis of ergodic partitions. This analysis necessitates a third limit, where you sample more initial conditions. This demonstrates the added complexity when dealing with nonlinear systems, showing that more limits are needed to capture the system's behavior accurately. The doubling map is a measure-preserving system, meaning that it conserves the measure like area or probability over time. However, it is not invertible, and its spectrum is the entire unit disk. Using methods like extended dynamic mode decomposition to compute this spectrum requires 2 successive limits. After gathering a large amount of data, you need to project this data onto a basis, but significant regions of the spectrum may be missed, and the process can become unstable. This example warns about the pitfalls of current algorithms and the importance of finding robust methods for spectral analysis. Koopman operators offer a promising approach to studying nonlinear dynamical systems by transforming them into a linear framework. They enable the use of linear techniques to analyze complex behaviors across various fields. However, the challenges of operating in an infinite-dimensional space, along with the difficulties in identifying spectral properties, highlight the need for further research and development of robust algorithms. The examples provided illustrate both the potential and limitations of Koopman operators, emphasizing the importance of understanding the fundamental barriers in data-driven dynamical systems analysis. The study's results reveal both the potential and limitations of applying Koopman operators to the data-driven analysis of dynamical systems. The authors identified the exact barriers to robust Koopman learning and established a classification theory for computational problems in this field. They suggest several future directions, such as exploring other spaces of observables, partial observations, Koopman generators for continuous time systems, and boundaries for learning invariant measures and spectral types. This paper provides a comprehensive and detailed exploration of the limits and possibilities of learning Koopman operators, offering significant theoretical insights and practical guidelines for future research in dynamical systems.